Hello and welcome back, everyone. We are moving on to our second speaker this afternoon, and that is Dr. Ian Seiferling, founder and CEO of Adaviv, an MIT-connected startup company. Adaviv is a predictive agriculture and machine vision company with technology for uncovering hidden plant biometrics, helping growers prevent diseases, improve crop yields, and optimize crop quality. The title of Ian's talk today is Artificial Intelligence and Computer Vision-Driven Crop Visibility Tools to Improve the Yield and Quality of Indoor Cultivation. Please note that Ian will be available for discussion 4 to 5 today, however, most likely only limited time, I understood, Ian. So, Ian, thank you for joining us today, and over to you.
Great, thank you, Peter. Thanks for having me and us part of this event today. We're happy to participate and happy to meet all the folks at Corteva. And yeah, I'll try to stay as long as I can in those breakout sessions, but we're always open to talk at any point if what you see today is of interest. I'm going to share my screen and put up some slides. So bear with me 1 second. Yeah, and please feel free to ask questions or chime in at any point. I'll talk fairly informally, so happy to entertain questions as they come or clarification. But you know, what I wanted to do today, I guess, is just introduce you to our company, Adaviv, who we are, you know, what our product is today and what our vision for the future is. We're focused, as Peter alluded, on indoor and greenhouse agriculture. So that's the market that we focus on in terms of building our products for and the environment that we work in. And you know, we're really excited about that space because, you know, it offers a lot of opportunities to grow higher yielding crops and more valuable crops and also mitigate, you know, the effects that we're seeing with climate change and weather. You know, it gives you that extra level of control over the environment. And so, you know, in that way, it offers, we think, a lot of tools, extra tools potentially for growers to get the most out of the plants, get the most yields and performance out of them. But at the same time, it's a lot of complexity, and so our job, or what we're trying to do, is bring those growers some, you know, extra visibility with our technology over the crop, over all the problems that might be coming up, and centralize that information and data so that they can, you know, understand that complexity better and really steer the crops towards yielding the most and the most consistency that they can get with that extra control that they have. We want to bring the plant to the center of the focus here and close the loop between the environment, the inputs, the controls, and the plant. And we think that's what's missing today is that the plant is really, you know, what the plant is telling us is not at the center of how we're making decisions. And often we're just, you know, doing it passively through the environment, but we can learn a lot by what the plant is telling us. And that's what our job is, I think, at Adaviv, is to translate that for the growers. A little bit about us. You know, we're a small team, we're a small company. We grew the company out of MIT. We're all researchers or students there at one point in the past few years. Myself, my background on the co-founding team is biology and data science. From Canada, originally from the Grain Belt of Canada, actually Saskatchewan. So I'm sure you guys probably know where that is just because of your agricultural expertise and knowing where all the grains come from. In Canada, Saskatchewan's a big one. My co-founder is Julian. He's our business development product manager, COO. He spent some years at McKinsey Consulting and did his MBA at MIT. Mo is our CTO and the brain behind our computer, our AI brain. He's a physicist by background, and Tom is an engineer and works a lot with sensors. And we all, worked together at MIT and met there, and we started the company there and have been working on it for about a year and a half, focused highly on product development. We are piloting and working with a few commercial growers in the Northeast. The other thing I'll note there is that we are working right now only with cannabis growers in indoor and greenhouse growing. We definitely, don't see ourselves or want to be a cannabis company, but we are starting with that crop, and we think the proof points are there in other crops and in vegetable production and leafy greens, and we will look to move into those crops as soon as we can. I am probably preaching to the choir here, but we all know that one of the biggest problems in agriculture is crop loss due to pest, disease, weather, all those things that are hard to control. And in greenhouses and indoor farms, it's no different. Even though we do have a little more control over the environment, there's still a lot of variability. And if we dive into that a little more specifically with our customers, it's very much true, and the data supports that. We talk to these growers, and they have a really tough time getting consistency out of their crops, even though they believe they're doing the same thing cycle after cycle. But there's still this large amount of variation that's happening in the yields, and in the case of cannabis, it's the quality or the potency as well that's really important. So whether you look as a whole, you get this lots of variation from crop cycle to cycle, or even when you look at the varieties that they're growing, they usually focus on a few varieties, as do most growers, and it's no different for those varieties that they focus and they know really well. They still have a lot of variation in what's yielding. Sorry. And we think that a big part of that, if not like most of it, is due to the fact that they just don't have the oversight over the crop that they need to be able to actuate, be able to address problems when they come up. So they miss pest and disease outbreaks really frequently. And because there's so many hands touching these plants and there's a lot of tech going into it, a lot of energy put into them, there's a lot of sources for human error and equipment failure as well. And because we're pushing these plants so hard to yield so high, just missing those for a few days is already having an effect on the yield for these high value crops. And so that's the problem we focus on and where we want to help. And we like to say that we're bringing digital eyes onto the crop for the growers. So at the very high level, the value we're trying to provide is give remote oversight, so that the growers, the managers know where the biggest problems are every day, every week, so they can catch them early, fix them early, prevent those losses before they happen. And really, in the end, with this data, we want to drive continual improvement as well. We don't want to just say, you have an outbreak today. We want to help them improve continually. And so we really take this lean cultivation mindset, and we're trying to build that into our software. Not only collect data about the plant health, but how can we continually use that to build those insights into their SOPs, into their daily cultivation procedures, so that they can do their job better each time. What is the effective amount of de-leafing they need to do? What is the effective amount of water at what time? Continually improving those growing recipes and with data is at our core. Diving a little bit deeper in terms of how we do that, we have a software hardware integrated solution. Our focus is really how we deliver insights through the software. We want to build the best in class software, but it's really all powered by the machine vision insights that we collect with our crop scanner that we've designed and built for the greenhouse. We call it the Mantis. So it This is a multi-sensor array system that moves around the walkways of the indoor farm or the greenhouse. Very low footprint design, and it collects image data and sensor data at a really granular level. At each plant, we are collecting a lot of data through multispectral, through cameras, through environmental sensors as well. And that data goes into our machine learning pipeline that we have entirely in-house, and we work with plant scientists to identify where the biggest problems that are occurring, and so we can quickly ramp up and build models, algorithms that are able to detect those problems very early on. We focus from everything from just, is this plant performing well? Is it sick? Is there an anomaly to be detected? Just giving that level of insights already providing something they don't have today. But then when we do, we can also deep dive on a customer basis. We know they might, one customer might have a problem with pathogens, and so we've built models to predict those. Others might have a pest problem, and then others might find it more important to know some biometrics. How fast is the plant growing? What's the height? And we can measure all of these things, and we use our software to centralize that. So we bring in this new data stream, but we also work to integrate the environmental sensing. We don't want to provide a fragmented solution. We try to centralize everything into our software system. And we try to actuate on those insights in two ways. One is the software that works in the field. We call it the flock, the front line of cultivation. That's usually on a tablet. And that's like a compass for the growers to know where the problems are every day. But they can also use it themselves as a human in the loop to input data when they're scouting the crop, or when they see something wrong and they don't know, or they need to alert their team of an equipment failure. All of that can be accessed through this software application that is used in the field. But really to drive, decisions, to drive, what they do every week, to drive how they actuate, how they treat the plants that have problems. We deliver automated reporting and a management action board as well, where we try to centralize all this data and really make it visible. What's the biggest problem of the day, or what's the biggest issue of the week? Are the issues getting worse or better? Is the treatments working or not working? So we try to bring those insights really to the forefront so that they can go to their team meetings and have that data and insights firsthand. In terms of what's behind under the hood in terms of the sensing that we bring to the table, as I mentioned, it's primarily based on computer vision. That's where our expertise lies. We scan these crops, these rows of plants, typically on benches from above and from the sides, and our models output these frequency or detections of problems that are stress indicators that the plant is responding to, and we detect those. Down to the leaf level, I think the biggest topic of today was molecular stuff, and you probably heard some really fascinating science behind, using AI to discover new molecules, chemicals. We're kind of the level up from there. We're not directly detecting molecular pathways, but we are detecting the expression of those and through multispectral imaging and also visible imaging. So on the left, you see a room that had a lot of issues detected. It was oversprayed and had a lot of burning, and so the model really picks up on those. Other times it's small areas where we can find something very early and it's maybe invisible to the human eye. But what we do is try to make that, bring it out with these computer vision reports and identify the regions or down to the plant that is the source of that problem with these computer vision reports. I see the question of if the robot can work in vertical farms. It's a nuanced answer. today is, yes, it can, but we have a limitation how high we can go. And we've built the system to be very plug and play. So we didn't want to install infrastructure. We didn't want to install cameras all over the place and be really expensive. A lot of the grows, the farms we work with, they grow on single level or sea of green, they call it, benches. And so we don't need to go that high, but we also do work with some that use these tiered vertical systems. And we can sense most of those, but today we haven't focused on building a new design that can go as high as the top tier. So we can sense like up to 20 feet high up, but sometimes they have tiers that go even beyond. So, but they tend to be rare in terms of the frequency of those farms. We know it's part of the future development. We'll get there, but today we focus on non-tiered systems mostly. Yeah, we did. Another question popped up. Did we build the instruments? So it's we try to use off-the-shelf technologies or sensors as much as we can. We didn't build any sensors from scratch, but we do get, we focus really on high resolution, high quality data. So we try to get the best sensors on the market, and we've built the platform around it. So we've integrated those. So it's kind of pseudo out of the box. We've had to build the software around that. We've built the mechanics and the hardware, but we're not building the sensors themselves. And in terms of spectral bands, this is also ongoing experiment. One thing that is different about what we do compared to maybe a lot of what you guys might know in the conventional agriculture with drones and aerial imagery, you have sunlight. Here we have artificial lighting, or both, and we have to understand what is the impact of the different light spectrum that we're dealing with on the multispectral bands that we collect. So we collect infrared, near infrared, we collect thermal data, we collect depth and 3D mapping data, and we collect visible data. And we're getting a lot of good, good data from that, and providing, the growers this kind of visibility that's shown in this slide. It's already providing a lot of value that they don't have today. So just being able to show them where, this is the distribution of the health of your plants. This is the areas where we're seeing problems. This is where the healthy plants are. These are the targeted ones where, you need to be very aware an outbreak might be happening, or this plant is expressing like a strong stress signal. So we can do that today with the visible and with the near infrared, but of course we want to continue to understand those dynamics. We have the capabilities to include other spectrum. We just haven't had the bandwidth to really start to fine tune and explore those other bands and be able, because we know there's value in there. If we want to be able to differentiate a water stress from a chemical or a defensive response, we can, the more layers of data we can add in those other spectrums going to help with that. But today we kind of go after the low hanging fruit as a startup, and so we focus on the visible and the near infrared and some of the thermal data that we collect. Yeah, to define healthy plants versus unhealthy plants, we use a lot of ground truth data, and that's one thing that I think is good about the system we've built. And the growers are using the software as well to scout the crops, and we also sometimes label the data with our software in the field, so we know if a plant is healthy or not healthy based on some granular inspection by an expert. But we also are able to detect just abnormalities purely with the image data, with the visible data and the near infrared. So basically anomaly detection. We've built general like unsupervised models that are pretty good at detecting like, you know, is something off, is something abnormal about this plant relative to the others. So without even any ground truth data, we can detect if there's problems, and then we go back and try to validate that in the field. But at the same time, we want to do more controlled experiments. We have a NSF grant underway for looking deeper into that and run some inoculation controlled experiments, and also how can we actuate with our robotics, with our system too, using different types of treatments. But yeah, in the end, you know, we're trying to build this holistic solution that not only produces a new stream of data, but also makes it very actionable and allows the growers to continually actuate and continually improve on their growing techniques, and get to a point where they're less worried about their yield output, and where they can actually start to use the power of this data to experiment for generate new growing recipes. That's you know, one of our big you know, longer term visions. We want to be the operating system of the greenhouse and help generate new growing recipes where we can actually manipulate the inputs and to get a specific output. But going back again, you know, we are early stage startup. We have to focus on low hanging fruit, and that is identifying pest and disease outbreaks, just giving that extra layer of visibility over the crop health. And I think we have great results already with the pilot customers we've been working with. We see that our detection models are you know, surpassing 90% in terms of how many of the golden sets, how many of the expressions of stress that we know are in the image, how well is the models performing at detecting those. Well over 90%, which is much better than people are actually. And so we can also say that we're, you know, 50% better than most experts that are also looking at the same data and the same images. But also we know in the field that we're actually performing much above 50% than the growers in the field, because a lot of times they don't have the specific plant knowledge, or once you spend 20 minutes walking a room of 2,000 plants, after 10 minutes, things start to look the same. And so we know they miss a lot of stuff just by fatigue, like visual fatigue. And so we can do this detection and visibility at much broader scale, and much more consistently. How does that translate into providing value to our customers? Again, we're early and we're continuing to quantify and build case studies, but we have some great early results. One of the first kind of full harvest cycles that we operated with, they're using the software to scout. They're using the insights to target the treatments. We saw a 15% increase in their yield over the annual average for the same varieties that they were growing. So strong proof point that we are adding value. And also we're just simply detecting more things than they were. We know that before we were bringing these insights as their baseline, we're detecting 40 to 50% more plant health issues than they normally catch, whether that's pest or disease or underwatering, overwatering. We are bringing an extra layer of visibility they didn't have today. So that's the broad overview of us. Again, today providing that visibility on plant health, but tomorrow really becoming the operating system for the controlled greenhouse, so that less people have to have their hands on the plants, that we can really build an automated future farm, but one that has digital eyes on the plants and is actuating based on what the plants are expressing and telling us. That's our vision for the company. To wrap up, a little more about us and some of the support we've had. We've got a lot of great support from the MIT community. We're also part of several support systems or programs, Microsoft AI for Earth. We're in the agriculture stream of the Creative Destruction Lab in Canada. That's going to be really exciting for us. And we have some great advisors on the team too, from ex-Google ag tech guys to computer vision experts and horticulturalists as well. And the last thing, you know, I just wanted to leave up maybe to as a point of discussion. I know you guys are a very successful company with expertise across many of the fields that we touched on. You know, are there potential opportunities in what we're doing? And that's something I would love to hear from you all. But, you know, the areas of alignment that I could possibly see is of course in crop protection, but specifically like, you know, tying data-driven plant insights and visibility to the actuation, to the treatment. That's one, you know, we help the growers track the treatments, but we're not telling them what to use or what to do today. And so that's, you know, that's a loop we want to help close, is take those visibility and those insights, but really tie it to the targeted treatments that are going to be most effective, especially ones that are non-chemical, because that's important in greenhouses, and it's especially important in cannabis because they're not allowed to use really any chemicals. And second is, you know, is to hear from you. Are you exploring new crops? Are you interested in controlled environment agriculture and these new ways of farming and automation? Would love to hear what your vision of the future of automated farming is, what you guys are doing as part of that vision, and where we can work together. And yeah, that's what I wanted to share with you today.
Thank you for this overview, Ian. To your last point, there's actually a question on the Q&A regarding partnering. Do you plan on partnering with companies to develop models that detect particular characteristics that companies are looking for? And do you have plans to develop models at the embryo stage?
Yeah, no, great question. You know, again, we're in our early stages of growth, and so we've had to focus highly on what we do today in terms of, you know, just detecting the biggest problems in the grow. But we have built a system very, very agnostic, and we own the entire data pipeline in-house. So we have a team of annotators, we have plant scientists that manages that. And we try to work with our customers to understand what their biggest problems are, both past and present, and build specific models for those issues. For example, one customer has a russet mite issue. And so we're really trying to nail down models that can predict very early on that specific pest and disease and the expression of that. So yes, we're working there as we build models on top of our baseline, which is, you know, anomaly detection models. We want to continually like feed more data, more diverse data, because we think we have a great foundation and a platform to do that really rapidly. It's just a matter of working with more growers and collecting more diverse data. So definitely yes to the first part of the question. To the second part on embryo stage, I think, yeah, long-term vision, definitely we want to, you know, bring our expertise and machine vision platform to the breeding. But of course, you know, it's not been a focus of ours today. It's just, you know, it's not in our wheelhouse today, but we want to get there for sure.
Okay, thank you, Ian.
I think, yeah.
I just briefly want to mention our perspective from the Industrial Liaison Program. So if a person who asked a question, who posted it as anonymous, is interested in speaking with you, we will be happy to make the introduction.
Great, yeah.
Happy to host a private meeting or introduce you directly,
Yeah.
Ian and Eric.
Yeah. Yeah, the only thing I would add there too, maybe while I have the chance, is maybe a little post-embryo stage, but again, this is kind of a cannabis specific topic, but it applies to other crops as well. You know, they grow from mothers to clones, and more they're using embryonic breeding and tissue culturing. I think our first touch point there will be on the cloning stage, and we are starting to collect data there. And the goal there would be to give them good predictive power of how well like a clone will perform. So I suppose it's a phenotyping challenge, because they obviously they grow more clones and produce more clones than they are going to grow in the end. They kill some of them. And so if we can help them identify the best performing clones early on, but also the best performing parts of the mother plants, we actually helped the growers eliminate some of their pest problems because we were able to help them trace that pest back to which mother and which mother plant that pest was coming from. And that is huge too, because a lot of these pests, they're really hard to get under control because they're so tiny, and you don't know where the source is. So we do want to play a role there, like in the short term too, in the cloning stage and in the early stages of plant development, and how different diseases are spreading or where their source is from. So I hope that answers the question.
Ian, could you speak a little more to the artificial intelligence component of your algorithm? And perhaps not about the intrinsic mechanism, but more how does it add value and how does it give your company a competitive advantage over existing solutions?
Mm-hmm. Yeah, I think, with AI in this space, data is obviously really important. I think that's where we see a key competitive advantage is really in our data quality, and how fast we can build models to get that value, as you're saying, out of them. And so, for example, if we look at computer vision in this space, how it's being used, if there's other competitors, there's kind of two extremes in terms of data. You can go low cost, embedded or distributed sensors and even cameras, and put many of cheap sensors everywhere, as many as you can, or cheap cameras. But that has a limited value in terms of what you can get out of that data, especially when it comes to vision. If you put cheap cameras only, you can only, sense, who knows, 10 plants, 20, 50 plants per camera. In our case, with one sensing unit, we can sense thousands of plants. So, but at a much higher granular level, because we are collecting very high resolution plant level data. So to us, that's the differentiator, is being able to collect very high resolution, very high quality data, but at scale and at a cost that makes sense. We do have, we can look at one competitor of ours, an early competitor, but much larger, much more complicated, much more expensive hardware component. And so I think we're getting high data quality at the low cost. So we're trying to optimize those two extremes. And if we can build, diverse data sets with this high quality, that's where the differentiation, I think, lies, because we'll be able to get more powerful insights, early detection of health problems, plant growth, different structural metrics. We can produce those much higher quality, much faster, and it'll take, anyone else just a long time to catch up to the performance that we can achieve. And we think we've already are on our way to building one of the biggest, if not the largest, like high quality annotated vision data sets for cannabis. So we think a big differentiation lies there, and then building that data moat. And the other thing we're doing in terms of AI, like how do you make it, valuable beyond just predicting, a pest or disease? It's always, of course, as everybody knows, about how you can improve the performance, or how you can actuate, how what you do with that information. And in the customers we've seen, they're kind of growing through their growth cycle, and they set a grow up the way they want, but in between they don't really have a lot of different things they're doing. They're not changing any controls or inputs. And they don't know what they're going to get until they harvest. And it's kind of a big question mark every time they get the harvest and they put it on the scales. It's like, is it going to be good or is it going to be bad? And so in terms of how we're trying to provide value with AI beyond the computer vision, we're trying to also, we've just launched this dynamic yield forecast, for example. So throughout the grow, based on the issues that are coming up, based on what the plants are telling us, we predict the yield. Is the yield going to be, above average strong, or is it below average? And how can you correct it as quickly as possible? So I think being able to really narrow those predictions down to be really accurate is just going to require, continuing to gather a lot of data, bringing more data sources in, environmental data, and then we can also, really unleash the power of AI in that sense to do that kind of predictive, dynamic forecasting as well.
Yeah, so we got a couple of more questions. Perhaps we start with the last one of these new ones. This one is probably most relevant to what you just discussed. And the question is, roughly how many data point sets per crop does it take to obtain a good model?
Yeah, that's a great question, and I wish my CTO was here to answer it better than me. But it's a tough one to answer, like, very quantitatively. So, we've collected probably over a billion pixel data points to date, over 3 million, I think, plant images, for example. And it's where you measure that performance. So we can get, I think, good performance in detecting a stress signature fairly quickly after, I would say, 1,000 like really well annotated image sets. But our images are really big. That's the other thing. So each image is in a traditional computer vision modeling sense, each image is actually like hundreds of training points for us, because we subdivide the images. So with like 1,000 plant images, we can start to get good performing models. And we also do stuff, targeted annotation, active learning, some techniques that we've developed to boost the training so we can get better performance with less human annotated examples. And so that kind of adds to that and boosts it. But, if we, for example, go into a new crop, a new customer, I think with, after a couple of weeks of data collection, we can start to give them accurate models and good performance. And then in terms of doing that at a crop with multiple plant species, that's a really good question and a really tough one. Right now we do everything at the variety level, or in cannabis, they say the strain level, because we try to treat each strain individually. They can be very different in their growth forms and their phenotypes. So we do deal with multiple strains in the same crop, and that's not a problem. But they're very similar in how they express stress and disease issues. So it's a little different than saying it's multiple species. I guess in the long run, I don't have a great answer for that one. It's a very tough question to ask, but I think it's less about having many different species in the same crop. It's more about how much data on each species do you have. We could easily, I think, go into collect data, separate crops, separate facilities, separate species, build really good models, and then you can mix the crops, mix the plants. It shouldn't affect like how our performance is, but we do need that, to build data sets for those specific species.
Very good. Next question. Could you flip the goal of a software to track plant control over plant health over time?
Yeah, I just want to make sure I understand fully that question. So I guess the question is flipping it so that you are steering the crop based on the data,
What
the
you measure.
insights,
Right.
versus just detecting a problem when it arises. I think, yes, that's the goal. That's the goal of what we're after. I think we need a lot more data to get to that level because, you know, as you guys know, there's so many factors that affect yield and performance, environment, microenvironments, genetics, crop steering. So our goal is to get to that level where we can generate a growing recipe, or if a grower wants to, for example, we know that underwatering early is going to have a huge impact on the yield. But if you underwater towards the end of the flower period, the potency, the quality actually goes up. So it's understanding those dynamics. That's what we want to get towards. I think after, you know, I would say in 1 year, we want to be at a point where we can start doing that type of predictive growth analytics so that we can help them generate those recipes or experiment very rapidly. So if we want to experiment with changing some parameters, we can have good predictive ability on how the plant will respond, but it does take a lot of data for sure.
Okay. What would it take to build health indices that are applicable across multiple plant species that are grown together? Does each need its own model?
Right. I think I tried to answer that earlier when I was speaking to the how many data points per crop does it take to obtain a good model. I tried to elaborate like how you would transfer that into like multiple species. So I think it's a tough question to answer. I think we would have to approach it just species by species, build good data set, build good models for specific species. And I think if they're grown together or not, it shouldn't be a problem. We can identify like which plant is which through the data, through the imagery, and we just treat them separately. So it's about, I think, the same answer, like, you know, a few thousand data points, and we can have good predictive models in terms of you know, plant health, plant stress, or specific problems. But we have to deal with it kind of case by case. What we do today is we have a strain as an input, but again, like the strains physically they can look a lot different, but more like physiologically they are pretty similar in how they express stress. So it's just something we continually try to improve on through the data collection process.
Okay, very good. Any more questions? Please type in the Q&A window. We still have time. Otherwise, I think we stop here. I don't see any more questions coming in, Ian. So let's stop. If you can join us 4 to 5 p.m. today, we'll see you then, hopefully. And in the meantime, we'll take a break until 3 p.m. When our next speaker comes online, who is Professor Ernst Frenkel from MIT Department of Biological Engineering. Thanks again, Ian, and I hope to see you later.
Thank you. Yeah, will do.